I am recording. And I'm going to start by sharing my browser with you, as always, to show you where we are in the course. Okay, we're currently here in week 10. And we talked about the definite integral when we met on Monday. And that was pretty much the area under a curve from some x value to some other x value. Okay, it's kind of like the accumulated total of the function, that the rate function, what it's generating. Okay, so you're always looking at a rate function when you do a definite integral, and you're trying to accumulate the value under it as you go along. And we talked about units, like if you've got a rate that's in miles per hour, right? That's your y value, your x value is hours. You multiply those together to get an area. So your accumulated value is in miles traveled, okay? So that was kind of what we did before, and we've been stumbling along with graphs, okay? So we've been doing a lot of estimating with graphs. And we're almost there where we could start introducing rules for doing integration. But technically, we're not going to do that until next week, okay? And the rules are going to be fairly straightforward because they're just kind of the reverse of the differentiation rules, okay? But we still are talking about concepts here. And it's important to understand exactly what this operation of integration is giving you. So what we're going to be talking about today is something called a fundamental theorem of calculus and antidifferentiation. So integration is another word for antidifferentiation, but they usually make the distinction between an antidifferentiation that gives you a function, like I start with a rate function, I antidifferentiate it and I get a total function, or I antidifferentiate a rate function and I evaluate it between x values and I get a number, okay? So we're going to talk about that a little more today. And we'll also introduce the fundamental theorem of calculus, which is what lets us do all this. Okay, so I'm going to be using this fundamental theorem and antidifferentiation notes right here. And if you give me a moment, I'll bring those up and share them with you. Oops. Okay, now let's share the content. Okay, everybody should be able to see my notes, fundamental theorem and antidifferentiation. Again, part of what I do is I excerpt things from the reading, and I try to slim it down a little because I know folks don't want to do a whole lot of reading in a math book. Okay, so that's kind of what this is, but with certain examples pulled out. Okay, so I try to share the highlights. Okay, so essentially we're going to start out with this fundamental theorem of calculus, which, if you think about it, is about 400 to 500 years old, discovered in the late 1600s independently by two mathematicians, an Englishman, Newton, and a German, Leibniz. Okay, so the two of them were kind of working on the same idea at the same time. That's part of the reason why there's multiple different notations in calculus. Okay, the differential notation was what Leibniz used, and the prime notation is what Newton used. So we're stuck with both of them, but each is useful in its own application. Okay, so let's take a look at this theorem. Okay, it says if I have a rate function, see this function right here, f prime of x dx, that's some sort of a rate function. And I integrate it between x equals a and x equals b. The way I do that is I take its antiderivative, okay, which is this f without the prime, okay, and I evaluate it at b, and then I do the same thing at a, and then I subtract the value at a from the value at b. Okay, b is called the upper bound, a is called the lower bound. So in other words, what this is saying is, to take a definite integral, which is what this is called a definite integral. okay? And it returns a value. When I say returns, I guess that I mean it gives you a value. Right? And that value is the area under the curve from A to B, the area under this rate curve. Okay? Now, I haven't told you how we're going to get the antiderivative yet. Okay? Because there are rules for that. Okay, so these are antiderivative functions. But just keep it in mind that the way we're going to get this value that we've been approximating by looking at graphs, right? Finding the area under a curve. Okay. Basically, what we're going to do is get the antiderivative function and then just evaluate it at the upper bound and subtract the value of that function at the lower bound. That'll give us the area. Okay. So we don't have to do the estimate stuff anymore. Okay. And here it is in words, okay? So again, this is important that this is a rate function, okay? They won't always put the prime on it, okay? And when you integrate it, the definite integral, it's giving you the change, net y units, okay? It's the accumulation, okay? The change in y that accumulates between the bounds. Okay, so it's the net y units. What are you accumulating as you go from A to B? Okay, and again, like I said, in assignments, they won't always put a prime here. So you have to remember that this is some sort of a rate you're integrating. Okay, anybody got questions on the terminology? Okay, or what these things are giving you, right? Okay, so essentially, okay, they're saying here is we can find exact answers for definite integrals, right? As long as we know how to go backwards from f prime to f, okay? And going backwards through the differentiation process will help us evaluate these. This is called antidifferentiation. But a lot of people just cut to the chase and call it integration. Okay, so if you have a function f and you differentiate it, you get the rate of change of f. If you integrate the rate of change of f, you get f back again. Okay, so these are like inverse operations. Okay, they undo each other. So again, I'm trying to explain it conceptually because that's what's going to help you actually use it in an applied way. Okay, you can do a million textbook problems and still not be able to apply this unless you understand what it's telling you. Okay, so let's take a look at a couple of examples. Okay, and again, what I had planned to do today is work through a lot of the examples here in the notes, and then I thought we could maybe have some fun with a Kahoot. I set up a Kahoot, which is like an interactive game at the end, and hopefully we can play that. We'll have enough time to play that. Okay. So let's take a look at example 1. Okay. If they give you the rate function here, okay, and they tell you f prime is 2x, what is its antiderivative? In other words, what function would you have had to differentiate that would have given you 2x? Okay, so what function f would have given you 2x as its derivative? Okay, so what's difficult about this is now you've got to kind of think backwards, okay? You have to say, well, 2x, let's see, that 2 would have come from the exponent, right? Because I would have brought the 2 down in front. Okay, so it would have been x squared. Okay, x squared would have been my function. Okay, and that certainly is true. Okay, problem is a whole bunch of functions, a whole family of functions would have also given you 2x, okay, as the derivative, like x squared plus 2, so will x squared minus 5, okay? So if you think about it, if I want to differentiate this, and I'll use the Leibniz notation here, okay, that would give me 2x, bring down the 2, drop the exponent by 1, and the derivative of a constant is 0. So that gives me 2x, okay? If you try it with the other one, where f of x is x squared plus 2, and you differentiate that, you're going to do the same thing. You're going to bring down your exponent, drop the exponent by 1, and the derivative of a constant is 0. So that's also 2x. Okay, so what happens is we have a whole family of functions, namely x squared plus or minus a constant, that give us the derivative 2x. So if we're anti-differentiating or integrating 2x, well, we get a whole infinite family of possible answers, okay? Because all of those functions would have given us the same derivative, okay? So the derivative tells you, yeah, it's a quadratic, but it doesn't tell you about exactly where it is. In other words, plus or minus something moves it up and down on the y-axis, okay? So you can shift the graph up and down and not affect the shape. So its derivative, its rate of change, is going to be the same, okay? So let me put that over here. I'll say it depends on shape, not location. Okay, so you can take a quadratic like x squared and move it all over the coordinate plane, and its derivatives would still be the same because you haven't changed how steep it is or how flat it is by moving it, by translating it. Okay, all you're changing is its location. Okay, so if f has an antiderivative, okay, capital F, there are an infinite number of them, okay, and they're only different by a constant, okay? And we call the constant of integration. Okay, so when you're doing an antiderivative and you want a function back, right? Like I started with 2x and I wanted its antiderivative function, I get a whole family of them. Okay, I get a whole family. All right, and you have to put the c there because, well, we don't know what C is. You'd need an additional piece of information to determine C. Okay, so you need, okay, so you can think of it this way. When you differentiate, and I'm sure you've kind of maybe had this feeling as you went along, like, hey, we just lost a constant, you know? We lost a certain amount of information with the differentiation process, okay? And when we reverse the process, we come up with a variable C, a constant of integration, and we need an additional piece of information to get a numeric value back for that. Okay, we'll see that when we get to applied problems. But so far, does this make sense? Make sense so far? What do you think? Can somebody shout out in the chat? Is this making sense?
It's making sense.
It's making sense. Thank you, Gil. Okay, so here's the definition of an antiderivative. Okay. And again, it's just the function that you get when you undo the differentiation. Okay. So it's a whole family of functions, and they only are different by this constant of integration. Okay, just like we saw with 2x, when I anti-differentiated that just kind of anecdotally, right? I didn't actually have a rule. I kind of used logic, and I said, well, what would have given me 2x? And I said, well, that 2 in front would have been the exponent. And I kind of reversed it mentally to say x squared, but it's actually x squared plus c. All right. So we're calling the function, the antiderivative, an indefinite integral. Okay, so this gives a function rule. Okay, an antiderivative gives a function rule. Okay, notice there's no upper and lower bounds on the integration sign here, on the integral sign, because we're not evaluating our antiderivative anywhere. Okay, we're just getting a function back. Okay, for a definite integral, you do the antiderivative process first to get the function, then you evaluate the function at the upper bound minus the function at the lower bound, according to that fundamental theorem. Okay, so think of this as the simpler of the two, where you get a function rule back. Okay, and then if you take it another step and evaluate it at bounds, if that's what they gave you, then you get a number, which is the area under the curve between A and B. Okay, those are two concepts that are really important to understand if any of this is going to make sense. Okay, so again, we have our friend the integral sign, it's just missing bounds. Okay, and there are some verb forms here, and people use these in different ways. Usually if I say anti-differentiate, I mean you're getting a function back. Okay, most people use the word integrate for both an indefinite integral where you get a function and a definite integral where you get a number. Okay, and that makes things a little confusing. Okay, I'll try to keep them separate, but I may slip into old habits of just using the word integrate. So if you're ever unsure of what it is I'm trying to do, please ask. Okay. So if you want to find the antiderivative of 2x, here's how it would look. Okay, you'd have the integral sign with no bounds, saying I'm getting a function, not a number. Then you'd have your rate function. Okay, so you have 2x. Now remember, the dx is giving you the width of the little rectangles. Okay, this is giving you the height of the rectangles, right? Because it's the function curve. And this is giving you the width of the little rectangles. Okay, that are the area under the curve. Okay. And again, what we're doing when we take an integral, and I'm not going into the details of the definition or proving anything, I'm saying we're making the little rectangles width approach 0, and we're creating infinitely many of them. Okay, that's what turns it from a Riemann sum into an integral. Okay, is letting those widths go to 0. Okay, and again, what we get back, okay, is a total function x squared. That's what would have given me 2x as a derivative, plus c. So I get an entire family of functions. Okay, family of functions with derivative 2x. Right? And yes, if you leave out the c, it's technically incorrect. Okay, so you need to put the c there. All right. Here's another one, okay? And here I'm just showing you how the notation is used. Here we want to find the antiderivative of e to the x dx, okay? You may remember that e to the x is that function that's its own derivative, okay? So that means I would have started with e to the x as the antiderivative. If I differentiated it, I get e to the x again, all right? But like always, I'm going to have an entire family of functions that have the derivative e to the x. Okay? Is that stuff making sense? Okay. All right. Another way to look at the fundamental theorem of calculus is to rearrange the terms a little with algebra. This might make more sense to you, okay? Here's the fundamental theorem the way it comes out of the box, right? The integral, the definite integral of a rate function from a to b is its antiderivative evaluated at b minus its antiderivative evaluated at a, okay? So if we want to think of it like this, and we say, the definite integral gives us the net change in the original function, okay? Net change, when you think of net, like in a business sense, you're usually doing a subtraction, right? Well, this is the subtraction right here, okay? So it's whatever the total under the curve was at A, take that away from what it was at B. So you're getting the difference in between, okay? So sometimes this is another way to say it, okay? The value of the total function at B is whatever you started with, okay? So this is value of the total function. Let me put words in here. Okay, and I'm using total function to be the antiderivative, okay? So starting value of total function at A, and this is the net change. Okay, so the amount you end up with is the amount you start with, okay, plus the net change in the function. Okay, does that part make sense? Okay, and all they did here was they solved for f of b by adding f of a to both sides. Okay, so they get rid of f of a over here, and it shows up on the other side of the equal sign with the integral and a plus sign in front of it. Okay, so you can get values for your antiderivative as long as you have a starting point and you know something about area. Okay, so let's take a look at this. Okay, here are a couple of examples. All right, suppose here's our function. Okay, they say capital F of t has the derivative lowercase f of t. Okay, so this is a rate function, right? Because they told us it was a derivative. Okay, and suppose we know the total function value at 0 is 5. Okay, find values for f of 1 and f of 2. Now remember, they're giving you the rate function, okay? And you know you're starting at 0 for the total function. So this is a rate function, okay? So we're going to use the second way to think about the fundamental theorem. Okay, we're going to start with f of 1, okay? And we're going to say that's f of 0 plus the integral of the rate function from 0 to 1. So that much. Okay, remember they said we could do this as long as we had some starting values and we knew something about area. Okay, well, if you look at what I just shaded in pink, okay, what I just shaded in pink is a triangle. It has the base of 1 and a height of 1, okay, and the formula for the area of a triangle is 1/2 base times height, okay? So you have to remember that, or you have to look it up. So I know the area of this triangle is 1/2 times 1 times 1. You can see it right here. Okay, so they're just substituting this area of the triangle in for the integral. Okay, so we're still doing this approximately. Okay, and we're doing it using graphs and what we know about area. Right, now remember, they told us that f, the antiderivative function evaluated at 0, is 5. Okay, and we know how much net change we accumulated. We accumulated 1/2 a square unit in net change. So we know that the value of the antiderivative at 1 is 5.5. Okay, so we did our starting value plus the net change. Okay, anybody have any ideas how we'd start finding f of 2? Can you explain how would we find f of 2, where f is the antiderivative function evaluated at 2? How would we find that using this strategy? Anybody have any thoughts? Nobody has any thoughts? Well, how about if we use this version of the fundamental theorem? Okay, we want to find f of 2, which is further along on the x-axis. We could start out by evaluating it at f of 1, which we just figured out. And then we can add the integral from 1 to 2 of our function for the net change. Okay, so here's the value of the antiderivative at 1, which we just got up here. It's 5.5. And then we can start accumulating more area, the area from 1 to 2, for example. Okay, that I can do the same way I did this one. Okay, that's the yellow area. And that's also a triangle. It's got a base of 1 and a height of 1. Okay, so let me put in my values. This is 5.5. Okay, and this is going to be 1/2 times 1 times 1. Okay, and that's 5.5 plus another 0.5, right? This is a half. So the accumulated value is 6. Okay. Anybody have a problem with this? Anybody concerned about it? Okay, so I'm asking, what would be the value of the antiderivative function to this? This is a rate function, and I'm trying to find the antiderivative function, okay, value at 2. Okay, no? Okay, remember, okay, a lot of you are probably confused by, wait, you told it was the area under the curve. Yes, but this time I gave you a starting value. Okay, see this up here? All right, we didn't know that previously, so we were just accumulating the area under the curve. Okay, if you know the starting value, okay, one thing you can think of is this is like knowing your constant of integration, okay? And so your starting value adds a little bit to your total area, okay? If I had left this out, or if f of 0 was 0, then yeah, I would have only accumulated 1 square unit of area so far. Okay, questions? Okay. Is this clear? You know what I'd appreciate, everybody? We've got, 9 of you on. Could everybody just say yes or no in the chat? Yes or no, I'm getting this, or no, I'm not. Just please type yes or no in the chat if you're following the discussion. Okay. Alrighty. Good, good. Thank you. Okay, thanks a lot, folks. I appreciate that. Okay. Now I want to introduce this other notation here. Okay. So here I'm saying a of x is the function from 0 to x of this f of t. So this notation could be a little confusing because you're seeing I got y here, I've got t here. Okay, rather than calling it y, we can call it f of t. Okay, so this is the t-axis. And what I'm doing here is I'm just moving my t slider over to some value of x. Okay, so like here, I'm saying, let it be a 1. Then I'm saying, let it be a 2. Then I'm saying, let it be a 3. Okay, so let me show you what this is. Just accumulating area. Okay, so I'll do some of them. Okay, this would be the integral from 0 to, and I substituted 1 for x. Okay, so all I'm doing here is finding the area under the curve from x is 0 to 1. Okay, or t is 0 to 1. Okay, if you look at that, that's my good old friend, a triangle, right, with a base of 1, a height of 1. So again, I'm approximating it using what I know about area and geometry. I'm not doing calculus here, I'm doing geometry. Okay, everybody see that one? Okay, how about you try this one? You try, what's a of 2? Okay, that's going to be the integral, right? You could start with what we already have if you want and just evaluate from 1 to 2. Okay, that's one way to do it. Okay, so I'll put the formula for you, right? Take what we've done, and now you're interested in this piece. Okay, so what I'd like you to do is you try that one, all right, and type done when you finish. How are you all doing? Are you stuck anywhere? I'm private messaging some of you. Okay, so please take a look at the chat and respond to me. Okay. Let's take another 30 seconds or so with this problem. Okay. If you're getting stuck, you can private message me. You don't have to message the whole class. Okay. Just in the chat, just pick my name and I'll get your message and nobody else will. Okay. All right. Okay, let's work this one together since I'm not really sure where you're stuck and you're not telling me. So I kind of have to guess. All right. So again, what we said we're trying to do is accumulate value under this curve, like accumulate area. They didn't give us a starting value, right? They're not telling us what capital F of 0 is here. So we're going to assume it's 0. All right. That way, if we want to accumulate the area under the curve, okay, what have we accumulated when we've gone from 0 to 1? Well, that's just the integral from 0 to 1 that this function is accumulating. So that's the area from x is 0 to 1 under the curve. It's a triangle, okay? And I use the formula for the area of a triangle, which is 1/2 its base times its height, to get that value, right? Its base is 1 unit, its height is 1 unit. So 1/2 times 1 times 1 is 1/2. That's the value of a of 1, okay? The antiderivative evaluated at 1. If I wanted to find a of 2, okay, what I have to do is start with the value at 1 and add the pink area, okay? So that's the additional value I'm accumulating as I go from 1 to 2. That means a of 2 is the 0.5 I started with plus the pink area. Well, what's the pink area? This is a square that's 1 by 1. Okay, so that's 1 unit. And then I have another triangle that's 1/2 times 1 times 1. Right, so this is the square, pink square, and this is the pink triangle. Does that much make sense? Okay, what is concerning me is if you're stuck, it's probably because you're not understanding what we're doing rather than you're getting stuck on the numbers. Okay. So it's important to understand we're accumulating area as we roll along. Okay. So we're starting out with a half. We're adding a 1. So now that's 1.5 plus another half. Okay. So that's a total of 2. Okay. Everybody all right with that? Okay, yeah, the equation is probably confusing because again, you've got this integral sign in there. Okay, and it's new notation. You just learned about it. Okay, so it's reasonable that that's confusing. But think of it conceptually, all right? You got a starting value and then you're accumulating area as you go to 1, that's 0.5. You accumulate another 1.5 units as you go to 2. What have I got now? I've got a total of 1/2 plus another 1.5. So that's a total of 2 square units by the time I get here. Okay. All right. So I'm seeing everybody saying, okay, that's better. Good. Okay. That's good. Right. Let's see some other stuff. Okay. Because again, a lot of the stuff that's in your text is highly conceptual. Okay. I know a number of you commented when we did the how's it going survey this week in class. A lot of you said, I need more worked out problems that are like the homework. And it's like, I understand that. But what's in the text is the conceptual stuff that is what's going to allow you to apply this. Okay, so I'd suggest when you do the homework, if you're totally lost as far as I don't know how to start, reach out and ask for help. Okay, and I can scaffold it for you. Okay, the worst thing you can do is say, I don't get this and throw the pencil down. Okay, that's not going to help. It's a struggle to learn anything new, but the important part in calculus is concept. We can leverage a lot of the computation onto software. Okay, but if you don't understand what these things are giving you, they're useless. All right, so please bear with me and the conceptual stuff, okay? And ask questions if it's not clear what's going on, okay? All right, so let's take a look at this, okay? They're giving us a graph and they're telling us it's a derivative. And then they're telling us use it to sketch a graph of its antiderivative. Notice the prime is gone. Okay, that satisfies the fact that when x is 0, so is the function value. We can ignore this for now. Okay, let's ignore this constraint for now. Just see if we can come up with an antiderivative function. Okay, you've done this example countless times, except you've done it going the other way. Okay, where I've given you a function and we've said, okay, what does the derivative graph look like? Okay, so now what we've got, here's the derivative on the left. Okay, and we want to know what function would have given us this derivative. So what you need to do is look at the derivative graph and say, what does this tell you about g? Okay, so look at the graph on the left. What can you tell from that graph? Okay, put some answers in the chat. Okay, or you can speak them if you want. Okay, what does the graph tell you about the function that has this as its derivative? Anybody have any ideas? Okay. Concave down. All right. Good for you, Richard. Richard's saying it's concave down because what he did, I guess, was differentiate this again. Okay. This is a straight line with a negative slope, right? So because the slope is negative, okay, that means its second derivative, the second derivative of g double prime, has a negative second derivative, so concave down. Okay. So let me write that down, negative slope, concave down. Good. What about this? This says g prime of 2 equals 0. What does that tell you? What do we know about the numbers where the derivative is equal to 0?
Is that a critical number?
A critical number, good.
Let's go.
Okay, x equals 2 is a critical number, which means it's either a max or a min. Now that combined with what Richard said, that it's concave down, what does it tell you?
The maximum.
It's a maximum. Good for you. All right. The other thing you can tell is, see the sign of the derivative up here? G prime of x is positive. Okay. Down here, g prime of x is negative. That tells you that g is increasing from negative infinity to 2. Right? Because the derivative sign's positive. And it also tells you it's decreasing from 2 on out to positive infinity. Yes? Okay. Now tell me this. Okay. What gives you a linear derivative? What sort of a function?
Quadratic?
A quadratic, right? Okay. So we know that g of x is quadratic. It's a parabola. It's increasing from negative infinity to 2 and decreasing from 2 to positive infinity. It has a maximum at 2, okay? And it's concave down. Okay, so you're looking at something like this, right? It's going to have a max somewhere up here, and it's going to be concave down like this, right? So now let me throw in this last condition, okay? The value of this function at 0 has to be 0. There's my graph, okay? Everybody all right with this? Okay, all of this information is what you learned during the first half of the semester, what this is telling you about this function. Okay, so again, it's the same business of, let me give you the graph of the rate function. Can you build the total function? Can you go backwards and give me the antiderivative function? That's all this is. Okay, technically, I screwed up my graph a little because you all know parabolas are symmetric, right? So if I was going to draw it like this, I should have extended my axis a little. Okay, and you would know this is an axis of symmetry. And if it crosses at 1, it should also cross at 4. Okay, so that's a better graph. okay? But again, the critical idea I wanted to get through was this condition anchors it on the graph. Remember, we said the stuff that the derivative tells us is it's a parabola. It has a maximum at 2, okay? And it's opening down. But it could have been anywhere on that axis of symmetry, okay? The thing that locks it down to a specific place on the coordinate plane is this condition right here. Once I have the second point on my parabola, I have one exact graph, okay? Everybody understand that? That locks it down? Okay. Anybody questions at this point? You can, again, you can always message me privately if you want to. Okay, anybody questions? All right. Okay, so we've kind of alluded to the fact that derivatives and integrals kind of undo each other. So here's kind of the relationship between the integral and its derivative, okay? If I have an integral of a derivative and I differentiate it again, right? I get back what I started with, okay? Another way to say it is differentiation, whoops, and integration are, like inverse operations. You could say they undo each other. Okay, so all this is saying is the derivative of the integral is the function you started with. Okay, now let's see how this plays out with example 5. Okay. All right, so they're saying the antiderivative from 0 to x of this function, okay, is here. And they want to know, all right, if I differentiate the integral, what do I get? Well, you get the function value, okay? F is measuring total area, okay? The derivative at 3 is telling you how much the area is increasing, okay? Okay, this is the same thing, okay? The derivative of the integral is just the original function. Okay, and they go through this whole big, long, drawn-out thing here that basically shows it. Okay, if we differentiate the integral, we get f of x. So f prime of 3 is f of 3. And you can see right here, that's 0. Okay. Does this part make sense? Okay, the idea of them being inverse operations. Okay, does that make sense? I mean, I don't want to hammer on it because, again, it seems kind of obvious that, if they're inverse operations, if you differentiate an integral, you get whatever was in the integrand, right? It's kind of like taking the square root of something squared. You get the thing inside. Okay. All righty. Let's try 2 more examples. All right. These are verified because, again, we haven't done any rules yet. Okay, so we haven't gotten antiderivative rules. So what they're doing here is they're giving us an antiderivative function. Okay, and they basically want us to take the derivative of it and see if we get back what we started with. Okay, so here's what they're saying is, if I differentiate this, do I get 3x squared? Okay, that's what verify means. If I differentiate this, do I get 3x squared? Okay, so let's give it a try. I'm going to use the power rule, bring down the 3, drop the exponent by 1. Derivative of 2 is 0. Okay, and you can see that these two things, here and here, are the same thing. Okay, so I know they gave me the right antiderivative. Okay, so f of x is x cubed plus 2. Okay, that's one value. Okay. Okay, why don't you try this one? Okay, you try example 7 and type done when you finish. You try example 7. Okay, so just verify. No, wait. Mhm. All I'm asking you to do is find the antiderivative. I'm not asking you to evaluate it yet. We can go back and do that. Okay, good. Yeah, sorry. I didn't evaluate it, so I'm not asking you. Just check it's the antiderivative. Okay, so what we have here is, yes, if I differentiate ln, I get 1 over x. So I know f of x is ln x. Okay, now let's go back to example 6. The second part of the problem says, use the fundamental theorem to evaluate the integral. Now, if you look at the bounds, the evaluation is from 1 to 4. Okay, so again, I do f of 4 minus f of 1. So it's always upper bound first. So that's 4 cubed plus 2 minus 1 cubed plus 2. Okay, and I'm putting this lower bound in parentheses, okay, to make sure I don't lose the negative sign distributing to both, okay? So 4 cubed is 64, okay, plus another 2 is 66, okay, minus, okay, 1 cubed is 1, plus 2 is 3, okay, so I have 66 minus 3 is 63. That's the value of the integral from 1 to 4. So you could see this is the antiderivative. That's a function. Okay, and this is the definite integral value from 1 to 4. Right, so that's the accumulated area under the curve. All right, what we found down here with ln, okay, this is the antiderivative. Okay, and then if I want to evaluate it from 1 to 5, I have this. I have f of 5 minus f of 1. Okay, and f is ln, so I have ln 5 minus ln 1. Okay, those are numbers, and you'd have to approximate them on your calculator. So ln 5 is about that. And ln 1 is, hold on, I think I did them all at once. Let's do them together. ln 5, let me fire up my TI so I can share that with you. Come on. There we go. Let me share that application. Okay, so now we can see the TI. I'll move that over here, move the video. Okay, I want to do ln 5 minus ln 1. And that's the 1.6094. Okay, so that's the total value. Okay, so that's how you do it on your calculator. Okay, ln is just giving you a value. It's saying, what do I have to raise e to get 5? What do I have to raise e to get 1? Okay, you can evaluate them all at once on your calculator. You don't need to break it up. Okay, this is an exact answer with the ln in it. And this is an approximate answer because I think you noticed I chopped off some decimals. Okay, so everybody okay with these? All right, we haven't actually done any antiderivatives that use a formula. Okay, we're going to talk about that next week. Okay, but if everybody's all right with this, I'd like to take a few minutes for us to try a Kahoot, okay, which is kind of a fun game way to practice what we did. So let me stop sharing and come back to the meeting, okay? And I'm gonna put the Kahoot, I'm trying to think of how to tell you to do this, okay? If you have a phone, okay, it's easiest to do on the phone. You can open a browser. If you have the Kahoot app, that's great. Okay, so I'm putting some directions in the chat. Okay, if you have a browser on your phone, open it and navigate to kahoot.it. All right, if you have the app, you can open the app. Okay, I'm sure you probably played this before. Okay, and what I'm going to do is I'm going to go to the Kahoot screen, okay, and bring that up for you. Okay, so take a minute and try to get in there. All right, I'm going to have you play one-on-one, okay, rather than teams, okay? As soon as you see the game pin come up, all right, I'm waiting for players. So as soon as you get to the Kahoot website or open the app, I see Alec, I see Juan, I see Miriam, Gil. Okay, we'll wait for a few more of you to join. Okay. See how many people are logged in. I have 10 people. 1, 2, 3, 4, 5, 6, 7, 8, 9. One more. Okay, we'll wait another couple of minutes, not a couple of minutes, couple of seconds. Okay, and then we'll get started. So I'm assuming all of you know how to play Kahoot. Okay, when it pops up a question, this is going to be like in quiz mode, and you'll have a bunch of options to choose from and a timer. Okay, so I tried to make the times long enough that you're not going to feel super stressed. Okay, and then it's going to accumulate points as we go along. Okay, so I think we have all 10 of you. Let me just count again. Yeah, we're good. So we're going to start. Yeah, I know it's a cheesy title. Okay, I'm going to close the chat so you can see everything. Okay, time's up. Okay, great job, guys. Most of you got the right answer, which is it's the definite integral of a derivative from a to b gives you the net change in the original function. Okay, remember we said you have a starting value and then you accumulate change as you go along. So great job. Next question. Here's the point totals. Okay, this one you'll have a whole minute to do, don't worry. You're just accumulating area, remember. And you're starting at 0. All right. Well, that was pretty good too. Most of you got the right answer. Okay. Remember, all you were doing was adding up the little blocks, and when they were split in half, they were half of a unit. So you could combine those two together. And you have a total of 4 square units as you get from 0 to 3. Good job, guys. Okay, here are standings. Okay, here we're giving you a derivative graph, and we want the graph of the antiderivative. Okay, and we also want the antiderivative to equal 0 when x is 0. Okay, get your answers in, guys. All right, this one was a little harder, and I can understand why, okay? But one thing I can say is almost all of you picked a quadratic. That was great. What I did with this one is I switched the line around, okay? So you wind up with a decreasing to an increasing, okay? So again, the fact that you realized the turnaround point was still at 2, that was great, okay? So just pay attention to whether or not you wind up with a function that's decreasing down to its minimum or increasing up to a maximum. If the derivative values are negative, you're decreasing, okay? And that's what I had in my graph of the derivative. Good job. Okay, here are our standings. Okay. Now here we are, we're taking a derivative of an integral. We want to know what f prime of 4 is. Okay, get your answers in, folks. All right. Well, again, as you can see, what we had there was we had the derivative graphed, okay? And they basically said, this is the integral of that graph. If I differentiate it again, remember, I get this function back again. So all I was asking you was for what was little f of 4? And that was 0, okay? All right. Last question is a true false. This one, you have only 30 seconds, so think about it. All right, awesome. Okay, all of you got it right, which is correct. Again, this is why we have a constant of integration, okay, when we take an antiderivative, because we get a whole family of functions that could have given us that derivative. All right, let's see our standings. Yay. Great job, guys. Way to go. Woo! Okay, so thank you for playing that with me. Okay, I'm going to go back to the meeting. Did you like that? Was that fun?
Yeah, it
What do you
was.
think? That was fun. Anything's better than listening to me talk for an hour and 40 minutes. Okay. Kahoot's a little challenging to use with math, but I think I figured it out. So we can do that from time to time. We can do Desmos student from time to time, anything that's a little more interactive than just talking, okay? So if you guys don't have any questions on this topic, you're good to do the homework for definite integral and this stuff on antiderivatives. Okay, if you have questions, you're always welcome to email me. Otherwise, I'll see you in class on Monday. Happy
Thanks so much.
Halloween.
Have a wonderful weekend.
Have a
Happy
good
Halloween.
weekend.
Don't eat too much candy.
No, we got class early.